Okay, as we remember from Chapter 2 or Topic 2 on the IB syllabus, on the most basic level, the periodic table is organized by the number of protons. In many cases, it looks like the mass number is what dictates it, but you will see anomalies within the periodic table that do not go in mass number order. So it is actually based on the number of protons, which, as we recall, is the same as the atomic number. So the periodic table, we're dealing with 3.1I1, 3.1A1, and 3.1 understandings 1 through 4. So the periodic table is organized by the atomic number, which, if we remember back to topic 2, we represent with a capital Z. So we have our nuclear symbol, and on our nuclear symbol we've got an example here of helium. If you look at your periodic table, you will see that helium is atomic number 2. And we remember that the atomic number is the same as the number of protons. So we have our Z number down here. And then on the top we have our A number. The A number is the mass number, which is the addition of the protons and the neutrons in that isotope. If we have a charge, so if it's not only an isotope of an element, but it's also an ion of an element, the charge would go here. And just a little recall for us, a 2+ charge means that it's lost 2 electrons, but we also know that helium is a noble gas, and that would rarely, if ever, form a charge or a compound. If there was 2, so if it was diatomic, we could potentially put a 2 down here. That's used more in nuclear chemistry than in what we're dealing with at this level. So the nuclear isotope for molybdenum-96, I would have to look at the periodic table and remember that molybdenum has the symbol MO. And I would write down that MO as my symbol. And then I would look at the periodic table and I would look for its atomic number, or the number of protons. And that is 42, so I write that down at the bottom, and the mass number is already given for me here at 96, so I just rewrite that. My mass number, my A number, is 96, my atomic number, my Z number is 42, which would be the same as the protons. And it didn't give me any information about it being an ion here, so we assume that it's an atom, so there's no charge up at the top. The atomic number is directly related to what's called the nuclear charge, so the charge of the nucleus. So more specifically, the periodic table is arranged by the nuclear charge, the number of protons, because we know in the nucleus all we have are protons and neutrons. We know that the protons are a +1 charge, the neutrons are neutral, so they're dealing nothing with the charge. So when we talk about nuclear charge, we're just talking about how many protons we have. So the nuclear charge is the number of protons that we have, which is clearly related to the atomic number. So my nuclear charge would be the same number as my atomic number. So going through the history of how we came up with the periodic table, how we got the design that we have today that's generally accepted by the scientific public, we started off with John Newlands in 1865, theorized that we can organize the first 16 elements by atomic mass in 2 rows, and that those 2 rows had similar properties. So he called it the Law of Octaves, like music. He noticed that those first 8 would be similar properties, and then the next 8 would have similar, or the next ones would have similar properties. So he'd say the first one here and the first one here, those are similar. The second one here and the second one here, those are similar. So he was just looking at how there might be similarities, but this was really limited, and it wasn't a very good way of visualizing what's going on, although it is nice to think of it as music. So Dmitri Mendeleev, this is generally who we think of as the father of the periodic table. He said in 1870 that let's organize the known 63 elements. Nothing with this first 16. Let's do 63 because that's what we know so far. So that's what he decided to organize. He got out some cards and he wrote down what they knew about the elements on the cards, and he started organizing them like a game of cards. At first he's like, well, let's do it by atomic mass. It seems logical because that was something they knew about the elements at that time. They knew atomic masses. Most things that we know now about the elements, they didn't know at that time. They didn't know about protons, neutrons, and electrons. So really all he had to go on was the atomic mass. And he started to group them based off of similar properties. He said, okay, these all react with water, our alkali metals. So let's put them all together in the same column. And we can see that this kind of overlaps with what we see on our own periodic table. We have lithium, followed by sodium, and then potassium. Here's where it starts to get a little funny. But those first three, he really had a good idea of what was going on there, based off of how they reacted with other things or how they behaved in a physical manner in their natural states. He left open spaces. This is what really made Mendeleev the father of the periodic table. He said, okay, nothing seems to fit here. I could technically put titanium over here by calcium because it's the next number, but the properties are not the same as they are with aluminum and boron. So that doesn't make sense. So what he did is he left this space and he said, okay, some element sometime somebody's going to discover, and that's going to fit in right there, somewhere between mass of 40 and mass of 47. And it's going to have properties that are similar to aluminum and boron. So he left these open spaces in a predictive manner that he hoped and thought someday would fill up and match perfectly. And he made these predictions, and he based them all on the properties that were surrounding them. Mendeleev came up with all of this idea without any of the knowledge that we have now about the structure of the atom. Again, those protons, neutrons, and electrons, and how the electrons are circling the nucleus. And he didn't know any of that. And he was able to come up with this much that looks so similar to our periodic table of today. So what was the main problem with Mendeleev's periodic table? Well, the biggest problem is that it was organized by atomic mass. Our periodic table is not by atomic mass because of those anomalies, those ones that don't actually fit in with the mass going in order.
He was born in Russia in 1834. Hard work as a youth opened up the college doors. He always tried to be the best that he could be and chose to make his mark in chemistry. And who told the elements where to go? Mendeleev, who put them in columns and in rows. Mendeleev, who was ready, who was able to make a periodic table. Who was that chemist? Mendeleev. He wondered if nature really had a master plan, if the elements had a pattern that one could understand. So he bought a bunch of cards, and on each one wrote the name of an element and its weight, and then he played the game. He put them all in order by their atomic weights, used their chemical properties to differentiate. Groups began to form, and despite some question marks, he managed to produce a simple periodic chart. Who told the elements where to go? Mendeleev, who put them in columns and in rows. Mendeleev, who was ready, who was able to make a periodic table. Who was that chemist? Mendeleev. At first, in 1869, the chart was not a hit, but that young Russian chemist was not the kind to quit. He revised atomic weights and staked his whole career, predicting that several new elements would appear. For a few years passed, and sure enough they came. Gallium, scandium, germanium were their names. Chemists everywhere were impressed with what they saw. There really must be something to this periodic law. And who told the elements where to go? Mendeleev, who put them in columns and in rows. Mendeleev, who was ready, who was able to make a periodic table. Who was that chemist? Mendeleev. So they call him the father of the periodic table, and his work gave rise to another kind of label. It's a name for element number 101. In honor of this man, they call it Mendeleev. And who told the elements where to go?
Okay, in 1910, so a little bit past Mendeleev, came Moseley. And what Moseley did was he took known elements and he shot X-rays at them to see what would happen. And he was able to derive a relationship between the X-ray frequency and the number of what he identified as our protons. So that left him able to organize the elements according to the increasing atomic numbers, which is what we do today. It decreased the troubles that there were with Mendeleev's table. There were some problems that they were trying to figure out. This helped with those. And it's the way that we organize our current modern periodic table. Even those elements that we're finding along the way, we're adding those on in atomic number. Some different ways to view the periodic table besides the kind that you have on paper form. We have this one, which you can't quite tell here, is a 3D model. We'll see that in class. It looks like a bunch of columns mashed up together. It's really a neat looking one. And then this is what the periodic table would look like if that F group that we normally have below the periodic table were mixed into the rest of it. And the main reason that we don't use our periodic table like this is because it's so long, which makes the font so small to be able to fit it onto a regular sheet of paper. You can see in my classroom a German periodic table that has it set up like this, where we have the S, the P, the D, and the F down here. We have it in that order, and you can just see how big it actually is when we get a font that is large enough for us to read. So the position on the periodic table is related to the electron arrangement. So we're trying to remember what we did in topic 2 with electron arrangement. We have the periods going across. So we've got the light colors here. Those are called periods. Those we sometimes give the letter N to, which I know can be confusing because we also use N to represent moles in our equations. And so it's as we're going across, so they're the rows, and it gives us the number of energy levels. So this is the first energy level going across, and then the second energy level, and then the third energy level. We get a little confused here. Remember when we have 4s2 and then 3d10. So we do have that little bit of variability there, but for the most part going across gives us the energy levels. And then if we go up and down, those are our groups. Those are the columns. You can remember that since it's going up and down, and we know that columns are used in architecture to hold things up, so we can remember that the groups are the columns, the ones that go up and down. And those give us the number of valence electrons. So all of the red ones here, the alkali metals, they all have one valence electron. Okay, electron arrangements. Thinking back to topic 2, we could write one for sodium. That's 1s2, 2s2, 2p6, 3s1. So it's right here. It's in the third period, and it's in the first group. So it has one valence electron. And then oxygen, 1s2, 2s2, 2p4, it's right here. It's in the second period, so it's got electrons in the second energy level. And it's in the sixth group across, so it has 6 valence electrons. And there are answers there. The valence electrons, remember, are the outer electrons, so the ones that are furthest from the nucleus. They determine the chemical reactivity properties and, in some parts, some of the physical properties as well. So relating to that last example, how many valence electrons are in each of them? We talked about that. Since sodium is in the first group, that means it will have 1 valence electron. And since oxygen is in the 6th group, it will have 6 valence electrons.